we are looking at the small perturbation theory, which is we are now looking at flow fields rather than integral quantities. And in the previous classes we had looked at velocity potential equation and small perturbation theory applied to subsonic flows. We are dealing with inviscid rotational flows, and therefore, these flows are isentropic also. And we had looked at the main steps that are followed to convert the velocity potential equation, which is a nonlinear equation in full, to a simpler linearized equations using small perturbations, that is, it is taken that a body in a flow, for example it can be a thin airfoil or a flat plate, it produces a uniform flow is here. So, V infinity, it produces very small changes to the flow, that is we have u prime, v prime, w prime, they are very small changes. So, the velocity v is written as v infinity plus u prime I plus v prime j plus w prime k, and a perturbation velocity was a perturbation potential was defined, which is u prime is dou phi by dou x, v prime is dou phi by dou y, and w prime is dou phi by dou z. And using this we converted a nonlinear equation into a linearized form, which had the form 1 minus m infinity square phi x x plus phi y y plus phi z z equal to 0. And we looked at the subsonic case, and there we looked at how we made a transformation of variables, so that this in a two dimensional flow this can be converted into in zeta eta coordinates into a simple Laplace equation equal to 0. And from there we understood that that this is a actually you can get these solutions, it is very similar to the incompressible Laplace equation, and from there we got the idea that Cp can be represented as Cp0 by 1 minus m infinity square. So, this is incompressible relations of Cp over any particular body such that it produces only small changes. If you consider such cases, then the incompressible relations can be extended to the domain of compressible flows, subsonic compressible flows, and the relation is given here, and this is known as the Prandtl-Gloretz rule, which is extensively used, applied, and there have been corrections later on, but the basic idea has not changed. Okay. So, that is for the case of subsonic flows, where if you know the coefficients, non-dimensional coefficients for incompressible flows, it can be extended to compressible domain using the Prandtl-Gloretz rule. Now, in this particular class we will look at supersonic flows. In supersonic flows, the value 1 minus m infinity square in that particular perturbation relation, it goes negative because m infinity is greater than 1. So, consequently we make a change, corresponding change is made. So, it is written as minus of m infinity square minus 1. So, then if you make it, then it will become lambda square phi x x minus phi y y equal to 0, where lambda is square root of m infinity square minus 1. This is applicable for flows which are supersonic, that is m infinity is greater than 1. So, now this if you look at this particular equation, it is a wave equation. So, a wave equation, the general solution is given by f of x minus lambda plus g of x plus lambda, where x minus lambda y and x plus lambda y represent specific lines in the domain along which there is a propagation of information. They are also called as characteristic lines. And if you look at this the angle which is dy by dx, it turns out to be 1 by lambda. You can take a general solution, say g is 0, phi is x minus lambda y, then dy by dx is 1 by lambda, which is 1 by square root of m infinity square minus 1, and that those are represented here, okay, on the top. They are left running waves, okay, dy by dx equal to 1 by square root of m infinity square minus 1. We can then look at the definition of a Mach angle. The Mach angle is nu is equal to sin inverse 1 by m, or sin nu is equal to 1 by m. Therefore, if you look at it and find out what is the tan of that angle, then you find that tan of the angle is actually 1 by square root of m infinity square minus 1. Okay. So, now this shows that these angles or these lines are nothing but Mach waves. Okay. So, in supersonic flow, if you have a linearized supersonic flow, this is now linearized, it is a wave equation, then there are particular lines along which information propagation happens, or there is a solution propagates in certain lines, and these lines are nothing but Mach waves, and Mach waves we have introduced very early on in the class. Now we see the actual implications of those waves. So, in any general arbitrary change or a initial profile is propagated along the Mach waves. Okay. There are two of them, because you have x minus lambda y and x plus lambda y. So, in general there are both left running Mach waves as well as right running Mach waves. Okay. So, the idea here is supersonic flow, the velocity the perturbation velocity potential equation becomes like a wave equation, and the wave equation is hyperbolic. So, this is inconsistent with the general characteristics of the flows that we saw, that steady supersonic flow is hyperbolic in nature. Even you find the same thing in the velocity perturbation equations also. So, similar to the subsonic flow, we are interested in trying to find out what is the pressure over the surfaces, and therefore we can calculate what are the forces that is occurring on such surfaces, examples like airfoils and so on. So, now that we have a general solution f of x minus lambda y and g of x plus lambda y, let us see what we can achieve from them. By differentiation, you can take, for letting g equal to 0, you can just take f of x minus lambda y, and you get u prime is dou phi by dou x and v prime is dou phi by dou y. While u prime is f prime, that is the differentiation of f, v prime has lambda associated with it, because now the variable is x minus lambda y. So, if you compare these two equations, we can see that u prime is v prime by lambda, negative v prime by lambda. Okay. So, this is what we get. Okay. And we know the boundary condition at the surface of the airfoil, that is, it should be tangential. So, dy by dx, the velocity is tangential to this v prime v infinity plus u prime. U prime is very small, so this is equal to v prime by v infinity. Okay, so and dy by dx is, and tan theta is approximately, so we are looking at small angles, small perturbation. Okay, so therefore we get v prime is v infinity multiplied by theta, it is dy by dx. Dy by dx is nothing but tan theta, but tan theta is approximately equal to theta for small angles. So, u prime becomes minus v infinity theta by lambda. Now, we had seen in the previous class that Cp for small perturbation can be written as 2 u prime minus 2 u prime by v infinity. So, now the u prime value that we had just arrived at, which is v prime by minus v prime by lambda, if we substitute into this equation, we get Cp is equal to 2 theta by square root of m infinity square minus 1. So, here we get a very important result. So, what we find here is that the pressure on the surface is just related to the angle of the surface at that particular point, or it is like a local surface inclination that is required. If we know the equation of the surface, okay, some equation of the airfoil, then its pressure at any point in a supersonic flow, in the domain of linearized supersonic flow, that is under small perturbation theory, which implies thin airfoils, small angle of attacks. Okay, so, under that conditions, the pressure depends only on the surface inclination, or dy by dx at every point. Okay, how much does that surface inclination occur with respect to the free stream, because here we took the free stream to be parallel to x axis. Okay. So, this is a very important result. So, if we want to find out what should be the forces on such on typical bodies, for example, here it is a biconvex airfoil is shown, which is symmetric. Okay. So, in the initial portion, this has it has a wedge angle which is small theta. So, over there initially the angle theta is it is moving the flow towards, turning the flow towards itself. So, it sort of compresses the flow here, and therefore, and this theta is positive, therefore, you get Cp 2 theta a by square root of m infinity square minus 1. Here this value becomes positive, but on the towards the rear part, there we find, since it is symmetric, you are getting similar theta values, but in the negative direction now. So, this is theta b, which is negative. So, Cp is negative. So, you find that Cp is negative. Okay. So, this is so in general you can consider many different such shapes. Earlier we had looked at shock expansion theory, and we had looked at diamond airfoil of this kind. You can consider the same in the context of linearized flows also, and this is also straightforward. The relationships will be very similar to what we are discussing over here, just right over here. But one more thing that one has to understand here is that here obviously, because on the y axis everything is symmetric. So, it produces no lift, okay. But at the same time, if you look at the x component of the force, then you will find that in this case there is a finite drag being produced. If you consider symmetric airfoils in subsonic flow, inviscid irrotational flows, then in such cases, in those cases there is complete symmetricity. So, both lift and drag are 0. It is the D'Alembert's paradox, because there the drag is being produced mainly by skin friction, which is not being considered in inviscid cases, okay, inviscid results. But here it is an inviscid flow. Even if it is an inviscid flow, if you integrate along the x direction, you will find that there is a drag is created, okay. That drag is because it is a supersonic flow and there are waves, and the behavior is completely different from subsonic flow, and this is what is often referred to as wave drag, okay. So, it is a pressure based drag, wave drag, and it is not a skin friction drag, okay. So, if you also look at how the Cp for subsonic flow, it is Cp naught by square root of 1 minus m infinity square, while for supersonic flow, this is for subsonic flow, for supersonic flow it is 2 theta by square root of m infinity square minus 1. So, as Mach number increases in the subsonic case, you find that higher and higher pressures or higher and higher Cp is achieved, because 1 minus m infinity square goes smaller and smaller. So, there is an increase here in the subsonic domain, but in the supersonic domain, as m infinity decreases, it is 1 by m infinity square minus 1. M infinity, if it starts increasing, this value increases, therefore, Cp will decrease, okay. And a comparison of these approaches with more exact theories shows that linearized theories are good for small angles of attack. For example, this is taken from the typical textbook. It is from John D. Anderson, both these images, and here they have looked at the difference between linearized theories and more exact solutions, and at angle of attack of around 4 degrees there is about 5%. Below that, it is very much same as the exact theory. So, such equations we can use for small angles of attack. So, or small angles and small angles of attack, which is thin airfoils, small angles of attack, okay. So, but it is a useful theory to quickly evaluate aerodynamic coefficients in both the subsonic and the supersonic domain before we go into other kinds of approaches which have better accuracy. So, towards the end of this topic, we look at a typical solution over a wavy surface. If you have a supersonic and a subsonic flow over a wavy surface, something of this kind, then how do the solutions? So, here you have a V infinity over here. The purpose is to distinguish between what happens in subsonic flows and what happens in supersonic flows, understand the characteristics of these different flows, these different domains, and also look at the solution, how solutions in general, solutions of the velocity perturbation equation. Here, of course, we consider h is very small. So, h is small. So, because it is a small perturbation, we are doing supersonic flow. So, we will just do the supersonic flow initially and then later on look at subsonic flows and see how they compare. And here so we already have seen that in supersonic flows the equation is a wave equation, it is hyperbolic in nature, and in general the solution is f of x minus square root of m infinity square minus 1 y plus x plus square root of m infinity square minus 1 y. So, you have two characteristics, left running and right running, and the appropriate boundary conditions are there, which is related to the gradients or dy by dx at the wall. So, you can put the appropriate boundary conditions and solve for phi. So, solution of the wave equation is done, and here for an initial contour which was h cos 2 pi x by L, phi we get as it runs as cos of this along the lines x minus square root of m infinity square minus 1 y. So, you can look at Cp, and here you find that Cp is going as sine of 2 pi x by L, Cp at the wall, okay. And dou phi by dou x will give you the u velocity, that is u prime, okay. So, you can get that over here, and at the wall it will be going as sine. So, the wall has a shape which is cos, but Cp goes as a sine function, okay. So, now if we try to look at the physical picture of this problem, what we find is that there are Mach waves that occur along the whole flow domain, starting right from the wall, going all through right up to infinity, and the solution is just moving over this or propagating over this particular lines along these characteristic lines. So, if you consider the crest, okay, so if you consider the point of the crest and this is y direction, then the solution is actually going along a line of this kind. So, the solution is actually symmetric along phi equal or characteristics lines which are x minus square root of m infinity square minus 1. They are not symmetric about y equal or the y axis, okay. They are not symmetric about y axis at any point. So, they are getting displaced or stretched by a certain amount along this characteristic lines. So, as a consequence of this these effects, so you can see that it is written over here the way the streamlines behave. The consequence is that the pressure, if pressure is integrated over the wall, okay, then you always get a finite drag for this particular solution. Also, this solution carries over all the way up till infinity, that is the effect of this wall in the supersonic flow is felt along these characteristic lines all through the domain, but only along certain directions, and this produces a certain drag, okay. This is something that we also saw in the previous discussion, that in supersonic flows the nature is such that you will get a drag even if all things look the geometry looks symmetric, that is because of the wave nature of the flow. Now, if you consider a subsonic flow of the same problem where the same contour is given, but now this equation is elliptic in nature, and the solution, if you look at the solution, you find that it contains an exponential term. You have some constants which are v infinity h square root of 1 minus m infinity square, but here you have a term e power minus 2 pi by L square root of 1 minus m infinity square y. So, if you look at this term, there is a exponential which has a negative term. That means this kind of a function will try to reduce the amplitude as you increase y. So, that effect is there. So, you get sin 2 pi x by L. In this case, you see that the Cp u prime and further Cp, they also follow the cos function, which is the same as the profile. That means they are symmetric over the profile, though there will be a phase difference. Okay, so there can be a phase difference, but it will be symmetric across the profile. So, as a consequence, if you integrate along the x direction, they all the forces will cancel each other, and hence you get drag is 0. So, this is something that again we had discussed earlier in subsonic cases. Inviscid flows, potential flows, you do not get a drag due to the pressure effects, mainly it is the skin friction drag. Okay. So, that is the consequence here, but the effect is more predominant in the streamlines. You see that there is a term e power something here. So, e power and a function of y, some say g of y or q of y, not to confuse. So, e power minus q of y. So, this function reduces the amplitude as you go away from the wall. So, that at a certain distance the effect of the wall is completely forgotten. Okay. So, if you look at the streamlines, they look like this. Near the wall they follow the wall very much, but as you go further and further away they change, and then again they come back to being similar to the streamline itself. The distance from the wall at which this particular change takes place, it varies as Mach number changes, and as Mach number is increased, the distance also increases. So, at very low velocities it will be quite close to the wall, but at higher velocities the influence is carried quite a long distance away from the wall, but eventually it dies down. But this is not the case with supersonic flows. So, if you now look at the comparisons between the two, the streamlines closely follow the wavy wall and are symmetric to the wavy wall in subsonic flow, but in supersonic flow the streamlines are symmetric about the Mach waves, not the wall. So, and the effect of the wavy wall, it dies out as distance increases, and that is actually a function of the Mach number in the subsonic case. But in supersonic flow there is no such exponential multiplying the solution, therefore, it extends to infinity. And here we also know that drag is 0, Cp is symmetric to wall in subsonic flows, but in supersonic flows drag is finite. This is the wave drag that occurs. These differences are arising due to the very nature of these flows. In subsonic flows it is an elliptic equation, and the information propagation happens in all directions, but in supersonic flow it is a hyperbolic equation, and information propagation happens only along certain directions which are Mach waves. So, this with this we come to a close on the small perturbation theory. It was useful to understand about subsonic and supersonic flow fields, their characteristics, how they behave, what are the differences in the context of inviscid irrotational flows. Now, supersonic flows, if you look at supersonic flows, they are hyperbolic in nature, and there are certain methods by which they can these hyperbolic equations can be solved exactly. They are similar to the wave equation, and we saw that there is the D'Alembert solution which follows certain characteristics. So, the exact velocity potential equation for supersonic flows can be solved in using such methods. They are known as method of characteristics. We will look at these method of characteristics for the supersonic flow because they are used for certain applications, particularly to look at the design of supersonic nozzles. The divergent, you know that a supersonic nozzle has a convergent and divergent portion, that is, if you are trying to accelerate from subsonic to supersonic flows. So, a supersonic nozzle is the divergent portion can be designed such that we get uniform flows at the end, at the exit, and that has to be carefully done by solving the flow field. So, that is done using method of characteristics, and we look at method of characteristics in the coming classes. Thank you.